Hello friends, welcome you again in this course on fundamentals of engineering physics, and today we are going to discuss about a new topic, that is Doppler effect in light and sound. So, in this lecture we are going to learn about the difference between sound and light waves, because we have to discuss about the Doppler effect in these two waves. So, that is why we should know about the difference between these two waves. So, brief update, because these are that familiar terms in the physics, the sound and light, but I will give the brief overview on this, and then we will go to the main topic, that is what is a Doppler effect, and then the daily life observations on Doppler effect, and then separately we will differentiate about that Doppler effect in the sound waves and Doppler effects in the light waves, and then some applications of Doppler effect. So, objectives of this particular topic, the first one is to give an overview on sound and light waves, the introductory one, and to impart knowledge on Doppler effects on sounds and light waves, one comparative analysis, and to discuss the daily life observation in this Doppler effect. And after attending this lecture, that learners will be able to understand the basic concepts of sound and light's Doppler effect, and to understand the effect of Doppler effects in our daily life, and learn some fundamentals mathematical formula to concern with the Doppler effect of sound and light waves. So, now let us compare these sound and light waves, and first there is some points to compare these two waves, but first one is this, that the nature of waves. The sound waves are actually the mechanical waves, and this means they require a medium to travel through, and they are basically the longitudinal wave. And the light waves, as far as the nature is concerned, light waves are electromagnetic waves, and they do not require a medium and can travel through the vacuum, and they are transverse in nature, and where the electric and magnetic field oscillates perpendicular to the direction of wave propagation. And one of the lecture, it is totally dedicated to this electromagnetic wave. Then the comparison of the speed of sound waves varies depending on the medium. In air at room temperature, the sound travels at approximately 343 meter per second, and it travels faster in liquid and even faster in solids, whereas the light waves, the speed of light, it is the fastest one, and it is in vacuum, it is approximately 3 into 10 to the power 8 meter per second, which is represented by C, and which is much faster than the speed of sound comparatively, and the speed of light decreases when it passes through different media, and such as water, glasses, and some other transparent media. Then the frequency range, and the frequency of sound waves that human can hear, that range from about that audible range, that is 20 hertz to 20 kilohertz, and the sound waves outside this audible range, this include infrasound, which is below 20 hertz, and ultrasound, which is above 20 kilohertz. And the light waves covers a broad spectrum of frequency. We have that electromagnetic wave spectrum, and known as that electromagnetic wave spectrum, and the visible light spectrum, which humans can see, that is in the range of 400 terahertz to 800 terahertz, and beyond this range we have that infrared, ultraviolet, X-rays, gamma rays, etc. And then interaction with medium. So, this sound wave require a medium to propagate, and can be reflected, refracted, and absorbed by the material, and these properties of this medium, especially that density and elasticity, that affect the speed and the behavior of sound waves. And whereas in the light waves, this can travel through the vacuum and a different media, and they exhibit behaviors such as reflection, refraction, diffraction, and interference, and there are so many different properties concerned with the interaction with the medium. And the properties of the medium, such as refraction and refractive index, affect the speed and behavior of light waves. That refractive index mu is equivalent to that C upon V, where V is the velocity in the medium and C the velocity in the vacuum. So, it give their own effect on that velocity of that light. So, the energy transfer, the energy carried by sound waves to mechanical energy, it is transferred through the vibration of particles in the medium, and it is longitudinal. So, that vibration obviously that will be in the direction of propagation, and light waves, the energy carries by light waves in this is in that is actually that electromagnetic energy, and it is transferred through oscillating electric and magnetic field. So, some examples of uses, the applications of sound waves are actually includes that communication, that is speech, music, medical imaging just like ultrasound and some sonar type devices, whereas the light waves have broad applications include as vision, communication, that fiber optics, medical imaging, X-rays and various technological such as lasers and microwaves, etc. So, now the question is what is a Doppler effect, because these are we have just compared that different properties of sound wave. So, before going to the details of that the Doppler effect of sound and Doppler effect of light waves, so we should know about that what is actually the Doppler effect. So, first let us imagine that you are standing on the railway platform and listening to the blowing whistles of a train moving past you, and the pitch or the frequency of the sound you listen as the train approaches you, that is higher than the pitch you listen at is moves away from you. This is the easiest examples of that Doppler effect. So, what this motion related frequency changes, that increasing frequency or decreasing frequency, this was first time observed and studied by John Christian Doppler in and this is one Austrian mathematics and physicist, and he has observed this, and that is why this is known as the Doppler effect with his name. In the simplest sentence, we can say that whenever there is a relative motion between the source of sound, means either that sound is moving towards source of sound is moving towards you, or you are moving towards that source of sound or moving away to that. So, that relative motion of that sound of source and that listener, the frequency of the sound absorbed by the listener is different from its actual frequency which is produced by the source, and this is known as Doppler effect. So, this Doppler effect is actually the wave phenomena, therefore, it occurs not only for the sound waves, but for any waves such as light and other electromagnetic waves. So, we will consider that relative motion in different observations. So, the relative motion between that source of sound and that observer. So, the first case let us take, that is the observed frequency when the source is at stationary and that listeners are moving. So, consider the point source S of sound at rest with respect to the medium. So, here because this is a mechanical wave, so there is we have to see the impact of that medium. So, that sound wave is at sound source is at rest with compared to that medium, especially here we are taking that air in which it is kept, and the medium is assumed to uniform, there is no density or mechanical property difference, and also at the rest. So, the source emit that sound waves, that will be the natural sound waves, original sound waves, and let us represent that by f, and its wavelength is lambda. So, the distance between these two successive compression, it is equal to its wavelength, because that waves coming out from that sun source, that will be in form of that wave front, and that will be obviously if you are taking that point source, so that will be that spherical type of wave front. So, the difference between that two successive compressions, that will be equivalent to that lambda, and we can correlate this lambda and frequency and value. This is that conventional formula, that frequency is equivalent to v upon lambda, where v is the speed of light. And now the listener moves directly toward the stationary source, and if we think that VL is the speed of that listener, then the relative speed of the source with respect to the listener becomes, that is, let us say v prime, and it is equivalent to v plus VL. V is the speed of sound, and VL is the speed of that listener. So, the relative speed, that will be that v prime, that is equivalent to v plus VL, and since the wavelength remains unchanged because that medium is uniform and the frequency of sound absorbed by the listener is changing, and the observed frequency, let us represent this is by f prime, then one can calculate this f prime is equivalent to v plus VL upon v multiplied by that the original frequency f, means that frequency when that source and observer both are at rest. So, f prime is equivalent to v plus VL upon v multiplied by f. This is that formula for that observed frequency. So, thus the observed frequency obviously that will be greater than the source frequency when the listener moves towards the stationary source. If the listener is moving away from the stationary source, then the observation will be obviously reversed. The observed frequency can be obtained by just taking the negative value of this VL, the speed of listener, and it is given by that f prime is equivalent to V minus VL upon V multiplied by f. So, now the second one, if we are observing that frequency when this source is moving and that listener that is at rest, or that will be in stationary form. So, when both source of sound and the listener, these are stationary, we are taking that frequency f. So, f we have taken is equivalent to V upon lambda. So, if we consider that the time between the emission of compression, because here we will have to calculate this time. So, this time this is inversely related to frequency. So, T is equivalent to 1 upon f. So, that is equivalent to lambda upon V. Now, the listener is stationary and the source moves directly towards the listener, and the speed of that source is Vs, which is actually less than the speed of V. So, in the time t, the first compression travels the distance V multiplied by capital T, where V is that speed of sound, and this is equivalent to lambda, that observed wavelength, and the source moves at a distance because at the same time t, that is equivalent to Vs multiplied by capital T, and as a result the distance between two successive compression that will be decreased, and that will be lambda prime, which is equivalent to lambda minus this distance covered, that is Vs multiplied by T, capital T. So, this lambda prime is equivalent to that is that observed wavelength, that is equivalent to lambda minus Vst, and therefore, the wavelength observed by the listener that will be given by this lambda prime, this is equivalent to lambda minus Vs, and when we put the value of this t time, so lambda upon V. So, by converting this in form of frequency, then we will get that after simple mathematics we will have that relation f prime, that is the observed frequency, in this case it is equivalent to V upon V minus Vs multiplied by the original frequency f. So, thus where the source moves toward the stationary listener, the observed frequency will be greater than the source frequency, and if the source is moving away from the stationary listener, the observed frequency can be obtained by taking negative values of that Vs. Obviously, simple mathematics is there. So, that formula will be modified as f prime is equivalent to V upon V plus Vs multiplied by f. Now, let us see the both are moving, means in the initial case we have taken that listener is at rest and the source was moving, and so in the second case source was at rest and listener was moving. This was the case. Now, let us think both are moving. So, when both source and listeners these are moving, then the observed frequency that will be that can be obtained by combining previous two relation, and that relation, that f prime will be equal to, that is the observed frequency in this relative case, and that is V plus VL upon V minus Vs multiplied by that original frequency. Here this VL, that is the velocity of listener, Vs, that is the velocity of the source. So, this Vs and VL, these are taken positive value if the source or the listener moves towards each other, if both are moving towards it, and likewise they are negative when source or the listener moves away from the others. So, if they change in the direction, then we will change the sign. So, that f prime, this is the final equation for equal to V plus VL upon V minus Vs and multiplied by f. So, let us take on the simple example for this formula we have just observed for different cases. So, let us say if I have one sound of frequency 1500 hertz and it is emitted by the source, which is move away from the observer and moves toward the cliff at the speed of 6 meter per second. Then we can calculate the frequency of the sound which is coming directly from the source, and second we can compute the frequency of sound heard by the observer reflected of the cliff, and we can assume the speed of sound that is equivalent to 330 meter per second. So, first case, the sound is and the source is moving away and observer is stationary, then we will use that formula f prime is equivalent to f upon V plus Vs multiplied by the original frequency. So, that f prime can be calculated by putting this value of that given value we can have this observed frequency is equivalent to 1473. And in the second case, sound is reflected from the cliff and reach observers, therefore, that f prime the formula we are going to use, and that will be equal to v upon v minus vs, because it is corresponding to the motion of source in the opposite direction with compared to the first one. So, that result will be equal to 1524. So, the simple mathematical formula based calculation, and we can get this result, and we can observe the change in the frequency in different cases. This is that Doppler effect related to sound waves. So, let us move to the Doppler effect of light wave. So, now we are familiar with that increase and decrease in the pitch or the frequency of the sound with the relative motion of sound and that listener, and this change in the frequency constitute that Doppler effect, and whose origin is directly straightforward. There is no special things, just we have simple mathematics, we can calculate easily. And the relationship between that the source frequency f and that observed frequency f prime, this can be given in a one uniform formula, that is f prime is equivalent to v plus vl by v minus vs multiplied by this original frequency f. And here this vs and vl, these are positive if the source and listener move towards each other, and they are negative when the source or listener moving away from each other. So, this is that formula, uniform formula. You can use this for every cases by taking special conditions. So, here actually this Doppler effect in sound, this depends on the relative motion of source and observer. Second, this appears to violate the principle of relativity. How? Because this sound waves occurs only in the material medium, and this medium is itself a frame of reference. So, if you have gone through that the chapter related to the relativity, then we have the concept of different reference frame. So, here we have one reference frame, that is the source, second reference frame, that is the listener one, and third reference frame in between, that will be the medium between that source of sound and that listener, and with respect to which that motion of source and observers are measurable. So, sometimes we feel that it is a complicated process, and it is trying to violate the principle of relativity. But in the case of light, however, there is no medium is involved, and only relative motions of the source and observer is meaningful. Then this Doppler effect in the light, this must be therefore slightly different from the Doppler effect in the sound. So, in order to analyze this Doppler effect in the light, we can consider again three cases. So, we just start one clock and that click that times per second and emits a wave of light with each tick, and we can examine three different situations. First one is there is that light source, it is that the propagation of light that is along x axis, and that listener of that observer, here that we should say about the observer, because we can observe this light and these are that visible light. So, that observer is moving perpendicular to the direction of the propagation of light. And in the second case, we will consider that the propagation of direction of light as well as that motion of that observer, that is in the same direction. And third case, that propagation of light is in along x axis, and that the motion of that observer that will be along negative axis, means these are approaching each other. So, the first case here we observer moving perpendicular to the line between them and that light source, and this we will calculate this proper time between tick, that is t naught, which is equivalent to 1 upon frequency naught. So, that we know that this time and that frequency, these are inversely related. So, t naught is equivalent to 1 upon frequency naught. So, between one tick and the next time, this t is equivalent to, because these are that mutually perpendicular direction. So, we can have this relation from if we consider that special theory of relativity here. So, we can think about that time dilation type term here. So, here this t is equivalent to t naught upon root of 1 minus v square by c square, where this v is that the velocity of observer in the perpendicular to the speed of light, and here c is the speed of light, and t is that observed time. And if we convert this in form of frequency, so in the form of frequency we can have this equivalent to that, just we will take that inverse of this. So, V is equivalent to V naught multiplied by root of 1 minus V square by C square. So, since these are mutually perpendicular direction, that is why this type of Doppler effect in this case of sound is known as a transverse Doppler effects. So, we have two types of wave motion, the nature of wave, that longitudinal as well as that transverse, and here that a transverse means that oscillation is perpendicular to the direction of propagation of that sound wave especially, and or the light wave especially. So, here since that observer and light wave both are mutually perpendicular direction, that is why we can say this is that a transverse type Doppler effect in the light. And this we can say by using this formula that observed frequency V is always lower than the source frequency V naught. This is according to this formula. Second case, when this observer rescinding from the light source. Now, the observer travels the distance t away from the source and between the ticks, and which means that the light waves from a given tick that will take Vt by C longer to reach time than the previous one. So, if that observer is at rest and this is that light source and the light is coming to that observer at time t, and if that observer is moving away from that source, so that light will take some additional time to reach that observer, and that additional time will be equal to that Vt upon C, where that V is the velocity of that observer, because at the same time that observer is moving away, that distance is equivalent to Vt by C. So, this that additional time we can that final time we can calculate, that capital T is equivalent to that original time t plus Vt by C, and again we will use that time dilation parameter here, that t is equivalent to T naught root of 1 minus V square by C square, and we will put this value and do some simple mathematics, that t is equivalent to T naught root of 1 plus V by C upon 1 minus V by C. This is in the terms of time. So, if we want to convert this in form of frequency, then we have to just revert this, because that nu is equivalent to 1 upon capital T. So, after reverting this, that formula we will have, that is equivalent to that V is equivalent to V naught root of 1 minus V by C upon 1 plus V by C. So, the third case, when this observer approaching the light source, and this means that observer is moving toward this light source. So, this observer they travel the distance t toward the source between ticks. So, each light wave take Vt by C less time, because if that light when that observer is at rest, light is taking time t to reach that observer, and if that observer is moving toward this light source, then this will take some less time, because it is moving toward that. So, that less time will be equivalent to Vt by C. Simple mathematics is here, and the total time now calculated is equivalent to capital T. This is equivalent to T minus Vt by C, and here again we will do some similar mathematics here, and that V prime is equivalent to V naught root of 1 plus V by C upon 1 minus V by C. Here one should I should just I would like to say here that I have just changed that notation for the frequency of sound and waves. In the case of sound, I have taken that f and f prime as the frequency, observed frequency and original frequency, but in the case of light, in general we are using nu as a frequency, so that we are taking that frequency notation as nu and a nu naught. Nu naught is the original frequency and nu is that observed frequency. So, what we are observing here, the observed frequency is higher than the source frequency. Again, the same formula hold for the motion of the source toward the observer, means that observer is either moving toward the source or source is moving toward the observer, we can use the same formula. So, this is the Doppler effect, which can be known as longitudinal Doppler effect, because that motion of observer and that light source both are in the same direction. So, that is why we can say this is longitudinal type Doppler effects. So, by adopting this conventional that positive is for the source and observer approaching each other, and a negative, that is for the source and observer rescinding from each other. So, by using this conventional rule, we can use this general formula for all the cases, that V is equivalent to V naught root of 1 plus V by C upon 1 minus V by. So, some example, and here this is one of the special example, because in social media also some good cartoons related to this Doppler effect is can be seen, and there one line is mentioned that only the physicist can understand, because that Doppler effect representation is there in that cartoon, where the change in the color is observed there. So, here one example I have taken from that book by Arthur Beecher, that concept of modern physics by Arthur Beecher. This is one of the special book, and I have taken this example from that book. So, here a driver is caught going through a red light, and the driver claims to the judge that the color he actually saw, that was not red, because of Doppler effect. And then judge accept this explanation, because both are the physics person, and yes, so this may happen. If it's original, that is originally red color, but you may have observed that green color. So, judge has accepted that explanation, but instead of that fines her for speeding at the rate of $1 per 80 kilometers. So, what was the fine? That calculation was there. So, the frequency of that green color, that was given as 5.6 into 10 to the power 14 hertz, and red color, that is 4.80 into 10 to the power 14 hertz. This is that frequency. So, that the vehicle is approaching to that signal, then we can use that formula to change in that frequency, because she has claimed that she actually observed that green color. So, that change in the frequency, that will be that green color frequency, and that original frequency what was actually that red color, that will be V naught. So, we can use this formula, V is equivalent to V naught root of 1 plus V by C upon 1 minus V by C. So, by putting the value of this original frequency and that frequency observed, we can get that velocity of that vehicle she was driving, that was almost near about that speed of light, that was 1.65 into 10 to the power 8 kilometer per hour, means she was flying. And that judge was familiar with that Doppler effect and physics related to this formula. So, he has calculated this, and velocity is this, and since this velocity calculated, that was exceed to 80 kilometer per hour. So, accordingly that fine will be 16499,999,920 these dollars. So, heavy fine was there because of this. So, now one of the important example, that is the expanding universe. This is that one can say this is the example application of that Doppler effect also. So, the Doppler effect on the light, this is an important tool in the astronomy, and stars emits a light of the certain characteristic frequency called spectral lines, and we know that all the characteristic properties of the stars, that is calculated on the basis of that light coming from that stars, and that is the spectral analysis, and that is known as photometric analysis. So, on the basis of that wavelength, we can know about that the components, material components of that star, that temperature and that distance, other things, and the motion of star towards or away from the earth shows up at the Doppler shift in this frequency. So, how the spectral lines of the distant galaxies of stars are all shifted toward the low frequency. Low frequency means that is a red color end, and the spectrum and hence this is called as a red shift, and such shifts indicates that the galaxies are receding from us and from one another. So, that since one observer, astronomer, it is observing that frequency from one specific star, and at the same time, and after 1 year, 2 year, 3 year at the same position, when he calculated, observed that frequency, and if that frequency is shifting in the negative direction, means it in the red color direction, then this is known as red shift, and it is estimated that galaxies are moving away from us, the stars are moving away from galaxy, even that all the stars and geometrical objects are moving away. So, this is known as expansion of universe. This is the best example of that application of this Doppler effect, and let us try to summarize this Doppler effect in sound as well as the light one. So, the speed of recession and are observed to be proportional to the distance, which suggests that the entire universe is expanding, and this is known as Hubble's law. So, Hubble is a great astronomer and he has observed this, and he has given that how that universe is expanding. So, just he created some points on a balloon, and when we expand that balloon by blowing that. So, with that the volume of that balloon increases, that distance between that dots marked dots, that distance are increases. So, Hubble has estimated that our universe is expanding like this, and the expansion apparently began about 13 billion years ago, when a very small intensely hot mass of permeable matter exploded, and event usually called as Big Bang, and that is that Big Bang theory. So, that is the astronomical point. So, present data suggests that the current expansion will continue forever. So, some examples, and we can get that distance galaxy in the constellation Hydra. This is one of the constellation in the ascending from the Earth is at 6.12 into 10 to the power 7 meter per second, and by how much is a green spectral lines of the wavelength 500 nanometer emitted by this galaxy shifted toward the red end and of that spectrum. So, since that we can calculate, we have that formula for the frequency, we have to just convert this for the wavelength, because in the data the wavelength is given. So, since this nu is equivalent to c by lambda and nu naught, that is equivalent to c by lambda naught. So, by converting this nu is equivalent to nu naught root of 1 plus b by c upon 1 minus b by c, we will have that new formula for corresponding to that wavelength. So, lambda is equivalent to lambda naught root of 1 minus b by c upon 1 plus b by c. By putting this value, that v is equivalent to 0.204 c and lambda naught is 500 nanometer, we can calculate lambda by doing simple mathematics, that is equivalent to 615 nanometer. So, this is in the orange part of that spectrum, and this shift, that is lambda minus lambda prime, that will be 615 minus 5000, that is equivalent to 115, and this galaxy is about 2.9 billion light years away. So, the Doppler effect is the change in the frequency, as a summary we can say, the wavelength of waves in the relation to the observed, who is moving related to this wave source, and it is commonly experienced with the sound waves, but also occurred with electromagnetic waves. So, this is the property of all type of wave, we can say. So, if the source and observer are moving towards each other, the observed frequency increases, and if they are moving away from each other, the observed frequency decreases and the pitch sound lower. So, approaching source, when an ambulance, as an example, ambulance with its a siren are approaching on observer, the siren sounds higher in pitch than when it is stationary, and receding source, as the ambulance passes and moves away, that the observer siren pitches drops. And we have that the concept of red shift and blue shift. So, in the astronomy in general we use this one. If a celestial object, it is moving away, its light is red shifted, means that its wavelength increases. If moving towards us, its blue shifted, means its wavelength decreases. And sound in a different medium, the speed of sound varies in the different medium, that is in air, water, solid, and this actually observe this Doppler shift. Some application we can conclude is so that in astronomy the Doppler effects help determine the movement of stars and galaxies, indicating whether they are moving towards or away from Earth. Radar and sonar, and this used to measure the speed of objects such as car by police, radar of that submarines by sonar. Medical imaging, Doppler ultrasounds in used to observe blood flow in the vessels. Okay, so thank you all for your attention, and we have just observed the difference in the Doppler effects and the slight difference in case of sound and wave. Thank you all.